We will now continue to part 7 of our simple SoC example, which is all about clock tree synthesis. So until now we had an ideal clock, some sort of a clock input that went to all of the flip-flops or all the clock sinks in the design. And that provided us with some basic timing analysis, which I just want to quickly remind you about. We had a max delay constraint or a setup constraint, which was T, the clock period, has to be larger than the flip-flop delay plus the logic delay plus the setup time of the flip-flop. So it was the TCQ over here plus the logic delay plus the setup time of the flip-flop. And we had a min delay that was the TCQ plus T logic has to be larger than T hold. So the TCQ plus the minimum combinatorial logic delay has to be larger than the hold delay of this flip-flop. And that was because our clock was ideal and didn't have any skew between the two flip-flops on a given path. But now we have to build a clock tree. So that same clock that goes in, it's not just going to ideally go with zero delay to all the flip-flops, but actually is going to have to go through some clock tree or some sort of a structure that's going to provide the actual clock to the flip-flops with some sort of an insertion delay. And it's going to cause skew between our launch flip-flop and our capture flip-flop, which I show here with this little red buffer over here, which is signifying some skew. And then we change our max delay and our min delay, so we actually add skew to the path between our launch flip-flop and our capture flip-flop. And that's because we decided to define skew in a positive way of, this clock arriving later than this clock. So that's why it's a plus of this skew. And we also take 2 delta jitter off of that. So if we add a jitter margin, some random margin in the worst case, then our launch clock will come out later and our capture clock will come out earlier. So we remove this 2 delta jitter. And I also have all these different margins, which are taken care of by the tools. And I explain in my lectures, but I'm not going to be really talking about the delta margin in this simple example. Then we also have the min delay, which actually becomes more substantial now. So we have our TCQ and our T logic. Now we have to take in our margin as well. And we have our hold, but our hold, it has in addition to it on the capture clock, we have this skew. And that's why this part of the equation can become bigger than that part of the equation. So we have to check hold after we build a clock tree. We usually don't have to check it before because usually the TCQ and T logic will be larger than our T hold. So in order to define our clock, we are going to create a clock tree spec. There are many attributes and constraints that guide the CTS into building our clock tree correctly or in the best way we can. And usually we're just going to create this automatically with the create clock tree spec command, which is going to go and look at our SDC and maybe look a bit more at our design and try to guess what we want to do and how to build our clock tree best. So it's really good to start with this create clock tree spec to create this automatic configuration, but usually you're going to have to tweak it and add some particular commands yourself. So some example commands that you'll see in your clock tree spec that's generated are create clock tree minus name clock minus source clock minus no skew group, and create skew group minus name clock minus sources clock minus auto syncs. And what that is going to do, it's going to create a clock tree and a skew group that are called clock, and they're going to start from the clock pin, whatever that is, and it's going to automatically see what the clock sinks are. We're going to be discussing that in a second, but it's going to take all the flip-flops basically that are driven by the clock tree and connect them to this clock tree and to this skew group, which are 2 separate things inside Innovus. Then there's all kinds of DB commands that we can do, like setDB CTS buffer cells, CTS inverter cells, CTS clock gating cells, where we provide a list of the cells that should be used in order to build the clock tree. And if you remember, we have these special clock cells which are balanced, and so we should be using them. There are all kinds of guidelines that I will go over later in how to actually populate these lists. Then we have other DBs, for example, setDB CTS use inverters true. That allows the clock tree synthesis to use inverters instead of buffers, which can save the extra inverter inside, but it can cause all kinds of trouble too. But usually we're going to actually use that. CTS max fan out, that's going to say what the max fan out of each one of these buffers is going to be. The target max capacitance and max transition time, these are DRVs. These 3 are DRVs that are specific for CTS, so they override the DRVs of the regular SDC or the regular lib files and put some sort of a CTS specific DRV target. There's also going to be some target skew, which is going to tell the CTS tool what target skew we want to try and arrive at. And we can also tell it to use something like useful skew. So set db opt useful skew cc opt. Extreme is going to say use extreme useful skew in order to really get a higher frequency. In addition, various components of the clock tree can be defined, and I'm going to go over those now. So the clock tree components that we have are basically the clock source, which we showed before. So this clock IO pin, in this case CLK, is going to be the clock source. It could also be the source of the PLL, could also be a clock source. But these are the clock sources, and the clock sinks, which are going to be the clock pins of the flip-flops that are driven by whatever the clock source is. So these are the clock source and the clock sinks. We have clock trees. So a clock tree is this virtual thing that is defined by Innovus, where we say, okay, we're going to create a clock from this source, everything that fans out from it, and that includes the buffers and all of the flip-flops that are on it. They are considered a clock tree. And that's one sort of a virtual type of definition that is used. But inside the clock tree, there are skew groups. So those are actually the list of clock sinks that we want to skew balance between them. And usually these things overlap, like they're equivalent. All of the flip-flops that are driven by the clock tree are going to be in one skew group, but you can override that and define different types of skew groups. So these flip-flops will be skew balanced together, and these flip-flops will be skew balanced together, but there won't necessarily be any skew balancing between them. We have what we call an implicit stop pin. So those auto sinks is actually going to go and it's going to traverse the graph of the clock tree from the clock source. It's going to go through buffers, and it's going to find where it reaches a pin that is defined in the lib file as a clock pin, and that is going to be automatically defined what we call a stop pin or a clock sink. There are what we call ignore pins. Ignore pins are pins that we build a clock tree up to, but we do not consider them for skew balancing. And for example, if we have a primary output that is driven by my clock source that is on my clock tree, it's implicitly going to be an ignore pin. So we will not be balancing this with these flip-flops over here. And we also have implicit through pins, which are things like clock gates or the inputs to clock buffers. Those are going to be pins that the clock tree is going to be built through. When I say that we build the clock tree through it, it means that we're going to check and fix DRVs, clock DRVs that go through this, but we are not going to consider it for skew balancing. So we will not be balancing this, even though it's a clock pin that goes through here, but it's going to be a through clock pin because it's a clock gate. So we're going to be balancing these guys. We're not going to be balancing this with that. God forbid, that would not be really nice. Okay, so how are we going to do all of this? We're going to use a setDB, give it the pin name, and do .cts sync type, and we have three types. Stop, so those are these guys that we can manually define additional places. We can decide that this is a stop pin, and then we'll skew balance this with all of these guys, right? So stop, ignore pin, where we can go and say, listen, I don't want to balance this flip-flop, so I'll consider this an ignore pin. Or exclude, an exclude pin is like an ignore pin. We do not skew balance it, but we also do not consider it as part of the clock tree, so we don't build our clock tree up to it. We don't fix DRVs or check DRVs on the way to an exclude pin. There is no way in Innovus to actually define a through pin as far as I could find. Okay, and the final thing is we have an insertion delay pin, which is when we have a macro. Okay, so say this is some sort of a macro that has its own clock tree inside, its own insertion delay inside. We may want to go and skew balance the clock pin of this macro earlier than what we balance these guys. So these guys, we want to balance them with whatever is inside here, with the insertion delay inside here. So we will define a float pin or insertion delay pin on this pin of the macro, using setDB of the pin, CTS pin insertion delay, and give whatever this insertion delay is over here. So in this case, 1.2 nanoseconds from this point to this point. It means it will try to balance this 1.2 nanoseconds before the balancing point of all these guys. Okay, so now we're at the CTS stage. So let's start stage CTS. And we either can create our clock spec and take it and use it, but I've already created a clock spec as I showed you in the last video. So we're going to read our clock config, and so we're going to source that guy. Okay, and then we're going to run cc opt design. And again, this is going to take quite a long time, so I'm just going to run it and take a break. So how about shielding and non-default routing rules, or NDRs? Well, I'm going to show you kind of the flow inside Innovus. So we have what we call creating route rules, and route rules are things like double width and double spacing. Those are rules that the router is going to use to route a certain net. Then we're going to create a route type. So a route type doesn't only have the route rules, but we combine the route rules with other things like preferred routing layers for that routing type if we want to apply shielding and so forth. So a route type uses route rules, but it also has additional information like preferred routing layers and shielding. And then we have setting the route type for different types of nets. And inside the clock, we have 3 defined types of nets. One is the top, one is the trunk, and one is the leaf. So basically, any clock net that is directly connected to a sink is called a leaf net. So that's the final net that goes from the final buffer to the actual flip-flop. On the other hand, we have the top. That's any net with a very high fan out. How high? Well, larger than the CTS top fan out threshold. So if we have, say this is set to 1,000, then any net that drives more than 1,000 clock sinks downstream will be considered a top net. Anything in between the leaves and the tops are considered trunk nets. And so the way Innovus treats this is we're going to set a different route type for each of these categories. So let's see how that's done actually with code. Create route rule. So we're going to create a route rule, one of these guys over here. We're going to call it CTS double width double spacing. And we're going to say that it's going to be having double spacing and double width. Okay, so we created the route rule. Now what we're going to do is we're going to create a route type that's going to use that route rule. So we're going to create a route type. This one is called the trunk rule. Okay, and it's going to use the non-default rule that we just created over here, which is called CTS2W2S. That's the name we gave it. But it's also going to add to this double spacing and double width things like the preferred layers. We want to route it between metal 6 and metal 7, and we want to shield it with VSS on metal 6 layer. So now I'm going to use setDBs to set which type of category over here uses what route type. So CTS route type top, that's a DB command. That's going to say for all the top nets, they're going to use top rule, which I defined over here. The trunk nets are going to use trunk rule, which I actually did define over here. And the leaf rules are going to be put on the leaf type nets. And we can also do this CTS top fan out threshold and define what the number is. So these are the types of things that we're going to do in Innovus to define shielding and NDRs, non-default routing rules, or well, you could call them route rules and route types combined together. They're somehow an NDR, something like that. So here are some recommendations for running CTS. So first of all, do not forget to specify the buffers, inverters, and clock gating cells with the relevant setDBs that I showed before. So that means we have to tell the tool which actual clock cells are going to be used for building the clock tree. Second thing is that we should prefer LVT cells, low threshold voltage cells. These could be ULVT, EULVT, all kinds of things like that, but whatever our fastest cells are. And the reason is we want to arrive at the lowest insertion delay possible. If we have a low insertion delay, it means we're going to usually have better options for skew balancing. We're going to be better adapted for corners and for on-chip variation. So this is kind of counterintuitive because we don't usually like to use LVT cells because they're very leaky. But the clock is always toggling, usually, unless we clock gate it. And therefore, the leakage is kind of secondary next to dynamic power for clock cells. So we prefer to have fast clock cells rather than low leakage clock cells. Next, we should stay away from the largest and smallest clock cells, and therefore probably in these guys we may want to remove, the largest and smallest clock cells in there. So the largest ones, they result in higher power and they can lead to all kinds of signal EM problems, okay, and regular EM problems, electromigration. The smallest ones are much more sensitive to corners, they're sensitive to SI, to noise from other nets, routing jogs, all kinds of things like that. So we don't want to use the largest ones or the smallest ones usually. The medium-sized cells, which like X4 or something like that, I mean, it depends on your library, they're important, so large ones aren't always used. Okay, do we want to use buffers or inverters? Well, often inverters result in a lower insertion delay in power, and therefore, really in advanced processes, usually inverters are preferred. We should limit the number of cells, so don't put all the million buffers you have in your standard cell library in here. Something like 5 per type buffers, inverters, clock gating cells, and gates, etc. And that's because of the runtime. We don't want the tool to go and check, a million cells for each type of buffer it wants to use. Multi-cut vias are very important. So multi-cut vias means that we have a lot of vias that are connected to, on clock nets and so forth. And again, we have this problem of electromigration. We have high current density. More vias means that the current density is lower, and then we can be better for electromigration. And padding near clock cells is a very common methodology that's done, also near flip-flops. So remember, these clock cells and the flip-flops, they're going to be toggling a lot. They're going to be toggling at a very low transitions, and therefore they're going to need a good DI to DT drop. So what we do is we often add padding, and then we can put some decap right next to these cells that will provide the charge we need right away in order to do this high-speed toggling. Okay, and so CC op design finished running. And we can go ahead and create the stage reports for that. So now when it runs timing, it's also going to provide us with hold data and violations and so forth. So we ran our reports, and we see here that at the summary we have also 1 picosecond of negative slack. That's really fine. Okay, at least that's in the BC analysis view, so that's for hold. And we probably have set up here too. We'll go and we'll look through the reports. Okay, and the CTS stage was also pretty quick, just a few minutes. So how do we run and debug CTS? Well, CTS is run with the clock op design command, and pay attention, there is also a CC op design command. In general, clock op design has now taken it over, but you can still use CC op design. So we're gonna do something like reset the CC opt config. We're going to source our clock tree spec that we made. We can also do just create clock tree spec and it will source it. And we then do check design minus type CTS. That's going to do a pre-CTS check design. And then we're going to run our clock op design command. Now, clock op design runs the CC opt tool, which runs clock concurrent optimization. That means it's going to build the clock tree, and at the same time, it's going to run timing optimization. In other words, in classic CTS, what we tried to do is we just tried to balance all the skew between the flops, but we didn't take into account any timing. And then afterwards, we had to run a post CTS optimization. In this case, it really iteratively runs and tries to do skew balancing, checks timing, and then does another skew balancing run, checks timing. It can apply useful skew and all kinds of other stuff. So that's what CC op does. In fact, nowadays in all of the commands, as I've been discussing in this series, we do this kind of concurrent optimization. So we do placement with concurrent optimization and routing with concurrent optimization. Well, the original one, I guess, was CC opt. So before CTS, we're going to run this check design minus type CTS as we saw here, and it may point out possible problems that we have with our clock tree before running it. We may want to run standalone CTS, so that's not going to do the clock concurrent optimization, but just the skew balancing. That can help us do things like build a balanced clock tree, check it out, and so forth. Do it with a lot less runtime. It can help us debug things and so forth. So that we would use the clock design command. It'll build a balanced clock tree, and it will not go through these timing optimization iterations. After the CTS, the clock is changed into propagated mode. So if you remember, when we were running synthesis and so forth, our clock was in ideal mode. We actually even wrote a SDC command set ideal net on the clock. Well, it's automatically, the tool knows how to change it into propagated mode. We do not have to run the set propagated clock command on the clock. It's automatically changed into that, and that means it is not going to be ideal anymore, and it's going to be accumulating the delay along the clock as it counts the timing parameters. So in addition, Innovus does something very interesting, which is how Cadence decided to deal with this problem. So the problem is that after CTS, we now have a delay on our clock that we didn't have before. And when we take our into reg and reg to out paths, they're going to actually be skewed, which may not be really true. There were all kinds of ways to deal with this, with virtual clocks and different types of things. But the way that Innovus decided to deal with it is it subtracts the average insertion delay from the primary inputs. So our source latency will now be negative, and we will see that in timing reports later. That will start from a negative type of a source latency. And this is very strange. So sometimes you don't want to use this, especially if you use something like a set max delay or something. So you can remove it, and it is kind of easier to read the timing reports. To do that, we do set db CTS update clock latency false. But when you see these negative types of source latencies, it's because the CTS tool is changing into propagated mode and putting negative insertion delay on the sources. So after CTS, we will often run opdesign minus post-CTS minus hold to fix the hold violations. It can also be run during clock opdesign, but we may want to do some additional hold fixings afterwards. So now let's discuss a little bit about post-CTS reporting. So there are a lot of reports that we can run post-CTS, and here are just some useful ones. So report clock trees is going to report a summary of all the defined clock trees. Report clock tree structure is going to give a detailed report of the structure of the clock network. Check or report clock tree convergence is going to look and see if there are many paths that lead to one output. Report skew groups is info about the skew and insertion delay in the different skew groups that we defined. Report pin insertion delays is a detailed report reporting the insertion delays at all the clock sinks. Report CC-opt worst chain is going to report clock chains with the worst negative slack. Report clock tree DRV is going to report DRVs in the clock network. So these are all kinds of reports that will spit out, and it's worth taking a look at and seeing if you have all kinds of strange things going on there. Okay, and timing reports should be generated, and this includes hold timing. And I'll be discussing timing reports a bit later on in the series. So report timing, okay, or just the super command time design minus post-CTS will create a whole bunch of reports in a certain folder. Or report timing minus early will check hold and report timing for the worst path in hold, or time design minus post-CTS minus hold will create the same types of reports, but for hold violations. So let's go take a look at the reports we got for post-CTS. So under the CTS reports, we have what was created during the CC-op design, and then we have my my printouts that I printed out with the end stage reports. So I have different things. So let's look at the setup timing, and we can go straight to the summary, and we see that we have positive slack, which means that life is good. We have the different path groups as we see: reg to reg, reg to Seagate, into reg, reg to out, into out, etc. Okay, we don't have any DRVs, so that's good and a very low density. Let's look at the hold timing. So the hold timing, this is the summary, and we have again 1 picosecond of hold timing. That's pretty much fine, right? So that means that things really worked. We have all kinds of other reports here that we just report skew groups, clock trees, clock tree convergence. You don't really need to put much attention to them. You can look through them, and they can give you all kinds of data and so forth. There's the check design command, which goes through a lot of things, and I just want to go quickly over it because I didn't before. So if there are any violations, it will say inside the check. So there's no power intent violation. We don't have any power intent in this design. Okay, placement, we have it says that these instances are not snapped to a row site. Well, guess what? These are all of our SRAMs. We wouldn't expect them to be snapped to a row site. In the design that's called opt, we have a whole bunch. So one of them is maximum transition is too small compared to maximum transition. So there's some sort of a small thing here. It doesn't look like there's a violation over here. Here's the sequential element cannot be touched by optimization. So these are these RC clock gates. These are created by Genus, and they're not able to optimize them, and that's fine. Okay, no constrained timing paths found. There's no violation. That's important. Okay, this one is the issue it has an issue with RC extraction. It's empty RC, and these are all of the pads, right? These are the IOs, which we just have a left of, so it can't do RC extraction of the internals of them. Okay, I guess that's why they're there. Route type is used for trunk or top clock nets, do not have a non-default rule. So it says non-leaf nets don't have a non-default rule. That makes sense. An auto-generated scaled skew target will be used for a certain certain delay corner. It says that the WC delay corner gets an auto-generated skew target, and I guess I didn't actually explicitly give a CTS target skew for that delay corner, which is something I probably should have done. It says here that more than half of the clock gates in the clock tree are instances of cells that are not in the clock gating cells list. And I guess here again, I didn't set up in the CTS clock gating cells attribute the names of the clock gates that are used, so I guess that's why they appear here in the violations. CTS skew target must be a numeric value. The CTS target skew attribute I didn't set up for the WC delay corner, I guess. And nets cannot be buffered for a certain reason. So the pad clock net, it didn't want to buffer it for a certain reason. It was buffered. We will see that in a little bit. So I'm not exactly sure what it's trying to tell us here, but it's worth going over these check design. It doesn't seem like there's anything very really bad over here. So again, we can go and look at the metrics. So I went over to the reports directory, CTS, and I can open the metrics HTML. It will show me again. It now added the CC-opt to the metrics over here, so I can go and I can look through what happened over here. I see that it added about 200 instances between placement and between CTS, which makes a lot of sense for clock buffering and so forth. The next thing I want to just show you quickly is the clock tree debugger. So Innovus provides this really nice tool which you can open with GUI OpenCTD or go to the menu Clock, CC-opt Clock Tree Debugger. And we can see over here the debugger with some windows open. So we have what we call the key panel and the control panel and the main panel inside and the world viewer on the side. Or I'm just going to zoom in kind of on the main part of this clock tree debugger, the clock tree viewer. And what we see here is our clock tree. As you can see, there's a lot of stuff going on here. So first of all, looking from top to bottom, this is the insertion delay. So here at the clock source, we have a 0 insertion delay, and it goes and it rises into, in this case, 2.3 nanoseconds. Okay. The clock root is over here at the top. There may be several clock roots. Each clock tree will actually have a separate clock root. Okay. Then we have buffers. They look like buffers over here. They can be inverters or buffers. So you can see that there are these buffers along the way. And then we have other types of gates, which are clock logic. So they can be all kinds of clock gates or ANDs or muxes or different things like that maybe here. And finally, we have the clock sinks, which are these red guys at the bottom. And you see that they're skew balanced. For some reason, some of them are not skew balanced. And finally, I have this thing called the clock tree debugger. So let's copy that over here. GUI OpenCTD is going to provide me with something very cool. This is the clock tree debugger. By the way, I could have gotten it by going to clock, CC-opt clock tree debugger, OK, and it opens me the clock tree UI. So this shows me the clock root over here, which is pad clock. It put 2 buffers over here for building the clock tree. Then they broke off. I have a clock gate over here. I guess that's a clock gate probably, right? And I have an AND gate over there. And I have different things, and I see that everything is pretty nicely skew balanced. For some reason, these flip-flops are not very skew balanced, but I see that how my latency goes, and actually it gets about 2.3 nanoseconds until I get to my flip-flops. But this is like looking at and going around my clock tree and understanding what is going on. So it's really nice to use this clock tree debugger to look at things. So in general, I could do hold fixing with opt design minus post-CTS minus hold. I will skip it for right now because we saw that we don't have any hold violations at this point when we finished our CC opt design.